So I want to look at the daily problem yesterday, aka today if you're looking through my video history. I recorded this, I uploaded it, posted it to Reddit, and then I realized the audio wasn't working. So I have to re-record it a day late, or 27 minutes late, but what are you going to do? So the problem is we have these two words, and we want to have the minimum number of operations to make them be the same. And we can do three things. We can insert a character into a word, we can delete a character from a word, and we can replace a character in a word. So first things first, this is a DP problem. A lot of the challenge of this problem is realizing that. And there's a couple of hints. The first is this says minimum. DP, you're always kind of minimizing or maximizing some aspect of the input. And the second thing is anytime you have string manipulation, particularly when there's some sort of evaluation being done, such as these two words need to be the same. Or another example might be something needs to be made into a palindrome, something like that. That's also kind of a sign for a lot of these problems that it's dynamic programming. And the reasoning is as follows. Dynamic programming is you have a certain question you want to ask. Can you turn horse into ROS? And this question relates to sub-questions. For example, if you deleted H, that takes a operation. Is it any better to try and turn ORSE into ROS, as an example? Or you deleted this R. Now you have HOSE into ROS. How many operations does that take? So any given problem that you're given, such as horse into ROS, it has a relationship with those sub-problems that are the next step. If you did an operation, then pretend you asked example 3, which was, what about ORSE into ROS? And there's a lot of ways you can conceptualize dynamic programming. It shows up everywhere. You got to tackle it if you're going to be really good at DSA. One thing that people love to say, one piece of jargon, is something like the requirements to use dynamic programming are overlapping subproblems with an optimal substructure. I see that all over the place. People love to say that. And that's really jargony, but it does have a meaning. Overlapping subproblems is the important part. With all dynamic programming, the basic idea is that you maintain a cache, or you maintain, you memoize, or you tabulate. But at the end of the day, all of that falls under the umbrella of caching, aka storing answers to these subproblems that then you can use and you can call on multiple times to answer the entire problem. If we think of a really simple example, I'm not going to reinvent the wheel here with dynamic programming, but let's say we're looking for like the ith Fibonacci number. So for example, the third Fibonacci number is 2. The fourth Fibonacci number is going to be 5, I think, or no, 3. And the ith Fibonacci number is going to be the I minus 1th Fibonacci number plus the I minus 2th Fibonacci number. And so this is something that I bring up because for any Fibonacci I, let's say I was 100, okay, well, fib of 99 plus fib of 98, and then what's fib of 99 if it's here? That's going to be fib of 98 plus fib of 97. So we have to calculate fib of 98 twice immediately. And this goes all the way down, and next thing you know, you're calculating fib of 0. If this was 100, I think it'd be 2 to the 100 times. So that just wouldn't work. That would be like, there's no possible way this will ever run. As opposed to if you just stored, hey, the first time you ever see Fibonacci of 0, what's that? It's 0. Okay, cool. So then every time you call that, you don't have to recalculate anything. You just look at what you've already called, or you look at what you already saved. And so you wouldn't have to call 98 2 times, you wouldn't have to call fib of 97 4 times, you would just call them all once, and it would take pretty much instantaneous time. Okay, so bringing it back to this problem, what are these subproblems? What subproblems are we saving by not having to traverse a bunch of times? Well, the way I have it set up here, there's 2 things we need to look at. There's the index of the first word and the index of the second word. And where the way I have this set up semantically is to say we're looking at RSE and ROS. What's the minimum possible number of operations we could take to make these two substrings equal? And then if we calculate that, it would be 2, because we'd have to change this S to an O and this E to an S. Or we could delete the E and insert something here, like after this R. But either way, it's going to take 2 operations. Once we have that, then we say, okay, what about this? Let's step back one. Let's finish that recursive call and then go back up to the previous recursive call, ORSE and ROS. That one we can say, well, there's a lot of options here, but one thing we could do is delete the O, and then we would have this. So it would be this number of operations, 2 plus 1 for deleting the O. And then we would go up again and say, okay, if we wanted to do that, we would have to delete the H to get to this 3 operations that we know works. So then we could say, well, among other things, we could delete the H. And then once we get to the O, we could delete the O. And then we would have these 3 that are 2 operations away. That wouldn't be optimal. It wouldn't choose that option because there's a way that you can do it in only 3 operations as opposed to 4. But that's how each subproblem relates to the larger problem, the previous recursive call that called it. And that's one way people talk about this, is subproblems. And here it kind of makes sense because the quote-unquote subproblem is going to be horse and ROS. And then one subproblem is going to be, okay, well, what if you deleted the H when you're comparing this H and this R and you need them to like be reconciled somehow? And then it would be ORS and ROS. Another subproblem you could do is instead of deleting the H, maybe you delete the R. So you could say, okay, what if it's horse and OS? That's one thing you could do in the hopes of trying to get these to be equal. You wouldn't want to do that, but another one could be instead of deleting the H or the R, you could change it to an R. So you would have this be like that. And then you compare all of these and you see which one takes the least amount of time, which answer to this subproblem is the least. Here you would say, okay, we have this main problem, example 1, straight up. So what we want to do is we want to pass in this exact comparison into our depth first search and then recursively call and say, what if we deleted the H? So that's one operation that now we've taken. And then how long does this take optimally? Because whatever this is, it's going to be that plus 1 if we delete the H. And we already went over this exact example. This is 3 operations. So this is going to be 4. If we deleted the H, then that's going to be 4 operations at best. If we tried, instead of deleting the H, deleting the R, that would be this, which I think would be much worse. That would be like 5 operations maybe. Because we would delete, no, I guess it'd be 4. You could delete the R, you could delete the E, you could delete the H. So this would also be 4. And then we say, what if we tried to change the H to an R in order to make that equal? And then in this situation, if we tried to change the H to an R, then what's going to happen is it's going to say, okay, we changed the H to the R. These are now equal. So in this situation, we almost can pretend like this prefix doesn't exist. We can just then compare that. And that's exactly what this does. So if we go through, we can see all these minima, all these minimums being taken, and it's pretty much going through these exact choices each time. And there's a couple things to realize. The first thing to realize is that inserting a character is exactly the same thing as deleting a character. Because again, like here, when we, let's say this one is change H to R. Yes, it's true. Now we're comparing. You could also change the R to the H, but we're comparing this now. So that's true. But really, we can just say, actually, we're kind of just comparing this because the R's are the same now. We can just go forward. Those don't matter anymore. And in fact, that's another thing to realize is that if we come across characters that are already the same, we just can ignore them. We can be like, okay, well, now we're comparing these. And here you could just delete the R and delete the E, And that's exactly what the optimal solution is here. So then here we have a couple of options. Let's say now we're looking at RSE equals S. And again, it's not really RSE. This is like RO RSE and ROS, but because these ROs are the same, we can just ignore them. And in this situation, we could say, well, we could change the R to an S. If we do that, then this is great. And then the next thing we would compare is SE, and that would take 2. So in that situation, changing the R to the S is going to take 3 operations. Or we could delete the R, and then in this situation, we can skip the S's and then delete the E. So that takes 2 operations, deleting the R and deleting the E. But the main thing to say right here is that if we ever have a prefix of the same characters, we can just ignore them. We can just pretend like this problem is these words, even though it's these words at the end, but this is what we would want to modify because everything else is the same. And similarly, let's say we have an example like AAAB and AAA, yeah, like this. We want these to be the same. So in this situation, we could say, okay, well, delete the B. But I bet a number of people watching would say, that wasn't my first instinct. My first instinct wasn't to delete the B, but just add a B to the other one. Probably not, because we're mostly phrasing this so far in terms of modifying word 1. But that's the important part. You can modify both of them. So in that situation, adding the letter that we need to the second word, or whatever, the word that needs it, is the exact same thing as deleting that same letter that would make it match from the word that has it, that the other one doesn't. And that's why here, we're only doing 3 operations, really. Maybe 4. We're doing don't do anything. And we can look here and say, okay, if the characters are the same, then just keep going and compare the next characters. And this is the only branch that doesn't add 1, because we're not making any operation. We're just like continuing on. And in fact, not only can we do this, we can always do this optimally. There's never a situation where the characters are the same and you would want to do anything. And then we have this choice, which is saying, okay, well, if they're not the same, just make them the same. Just do this, except instead of the characters already being the same, you have to spend an operation to make the characters the same. So this is the replacing a character. And then here we're saying, okay, add 1 to J, don't add 1 to I, aka delete a character from word 2, delete the character from word 2. Or add 1 to I and don't add 1 to J, delete the character for word 1. And again, you could phrase this as insert the character into word 2, insert the character into word 1, but those have the exact same effect. And then finally, we've outlined these choices. And the way to think about this are these relate different states in the state space. And the states are what are I and J, or what are these substrings that we're comparing. Which again, you could totally have this be S and T in here. You could have this be like depth first search, and then instead of I plus 1, it would be like S at 1 and on. So skip the first character. Now we've seen it. Now just compare the rest of the substring. And T at 1 means, okay, skip the first character in T and compare the rest of the substring. I think that's like a little more intuitive, but 2 integers hash faster than 2 strings. So this saves a bit of time, especially when the strings can be a length of 500. So these are how we relate our states in our state space. So we start out, and our ultimate state that we want to find the solution to is, what if this is this word and what if this is that word? And then we relate and we say, well, that relates in these ways that we just outlined, in exactly these ways to, well, the answer to this and this is going to be 1 plus the answer to this and this. Or 1 plus the answer to this and this, if we decided to change the H to match the R. Or if we wanted to, the answer to this and this, if we decided to delete the R. And then it would take the maximum or the minimum number of steps from each of those, the most optimal of each of those. So each state relates to 3 different states, really. I mean, it's kind of 4 different states because of this. But you could easily kind of iterate through and just say, like, while s at I equals t at j, I plus plus, j plus plus, whatever. And those are all outlined. So now if you think about our state space or all of our subproblems as this large graph of interrelated states or interrelated problems that we're asking, we've established the shape of that graph. We know what it looks like. Every node has arguably 4 vertices to other nodes that are a given node is a given problem that we're trying to answer. And then these other nodes that we have 4 lines out to are the subproblems of that could be answered. And then we want to look at the minimum of those. And then the other thing you need for dynamic programming or to solve the state space is to be like, okay, everything's swirling around and around. What's an actual concrete answer we can give? And we see that here. We can just say, well, if you reach the end of both words, then you're done. Then return 0. If this was comparing 2 empty strings, you wouldn't have to do anything. And if we were comparing, let's say these were just the same, like this, what would it do? It would say, okay, is ROS equal to ROS? I don't know, but however long it takes to make them the same, that's going to be the same as if OS is the same as OS. Or however long this takes, because R is the same as R, this is going to take exactly as long. And then it's going to say however long this takes, that's going to be just as long as this. And then however long this takes is going to be the same as just nothing equals nothing, which is 0 operations. And then we can bubble back up and say, hey, this takes 0 operations to resolve. And even if they weren't exactly the same, even if we had these again, you would still find that there would be every single chain of solutions to these subproblems would eventually relate back to that base state, where it would say, hey, what happens? Okay, let's just go through. So what happens if you change the H to the R? Okay, and then sort of according to our rules, we can add 1 to I and add 1 to j because the R's are the same. And then we can add 1 to I and add 1 to j again because the O's are the same. And then in this situation, we could say, hey, this is too great of a length, so what happens if you delete that? And then we have that. Oops. And then we can say, okay, those are the same, so that's going to be E equals nothing. And then in this situation, we can sort of say, what happens if you deleted the E? So in that situation, then we get to nothing equals nothing. So in this situation, like this costed 1 operation, this didn't cost anything, this costed 1 operation, this didn't cost anything, and this costed 1 operation. So total, it's 3 operations. And we know that because this base state where these 2 empty strings are called, where I equals s dot length and j equals t dot length, this returns just 0 because nothing needs to be done. And then the other base case that really you wouldn't even need to include, but it's a kind of simple way to cut out early is just if one of the strings is empty and the other one isn't, then however many characters are left over in the non-empty string, that's how many like deletions we have to perform or whatever additions to the first string. So that would be like here, instead of saying what happened if we deleted E, what happens if we delete something from nothing, what happens if we change E to a character, we don't even bother with those. We just say at this point the only thing you could possibly do is delete all the characters in this string. So whatever answer there's going to be up above, we're returning 1, which then is going to be 1, and then 2, and then 2, and then 3. And with that, we've pretty much outlined it all. We have our state space, aka how all of our problems relate to each subproblem that that problem has. And then we just say, to go over the specific code, we say, okay, look at answer. To start out, it's infinity because we're taking minimums. And then say, hey, if the characters are equal, then just go to the next thing and don't do anything. If they're not equal, try one of the 3 things we can try and make answer the minimum between whatever it is now and however long this took. So answer in the end is going to be the minimum of these 4 things. And then just return that. So then whatever recursive call called this is going to be like, okay, if I did whatever choice led to this, now that's going to take answer operations. So then if the previous call didn't do anything to reach this state, then great, it takes answer operations for that. If the previous call did one of these, then it's answer plus 1. Whatever this returns 1 is added to that for the previous recursion. Yeah, and so we have that relationship established between the answer to a recursive call and its previous recursive call that uses that in these 4 ways. And then we have the base states, which are, how do you actually obtain any answer for anything other than just another subproblem plus 1? What are our base cases? Our base cases are you reach the end for one or both of them. And that's pretty much it. I mean, the only other thing to cover is this little at cache, which this is the dynamic programming part. This is a little just Python under the hood. This just says make a hash map, so make a dictionary where the keys are the inputs to your function and the values are the output to this function. And anytime you ever see an input that you already have in your hash map, just return the value at that key. So you don't have to execute all of this. You just say, hey, if we've seen I equals 1 and j equals 1, just don't even bother doing any of this stuff. Just return whatever the answer was there. And the only drawback here, there's 2, I guess. The first is that if you're going to say at cache and be lazy, which like I did, you can't do this iteratively. You have to do this recursively. It locks you into doing that. Not that that's necessarily a bad thing even for runtime complexity, but you got to do it recursively because cache doesn't work with iteration. That kind of loses its meaning. And then the second thing too is that these have to be hashable, which means they have to be immutable. They have to be integers, they have to be characters, they have to be strings. They can't be like a list, because a list you can't hash as a key in a dictionary. You could have the output be a list, that would be fine, but the input can't be a list. And if you think about it, that kind of makes sense, because a data type that's mutable, such as a list, if you had that be an input, this is saying, oh, we've already seen list nums or whatever. We've already seen that list, so I have an immediate answer. But the problem is, it's like, well, the list could have just completely different elements because it's mutable. So there's some aspect of it that's changeable. But that's fine. I can't really think of a DP situation where the subproblem you're asking has a list as the input to a subproblem. At the very least, you can always change whatever sequence into a string if you really need to be able to hash it. And yeah, I would say that's the crux of a pretty quintessential recursive dynamic programming architecture here. And again, I think the really difficult part with this problem is recognizing that that's what there's a couple things to recognize. Recognizing that that's what you need to do. Recognizing that you never really need to insert. You could always just delete, or vice versa. And recognizing a couple of little things, such as replacing one character with the other is exactly the same as replacing the other character with the first. You could change this H to an R. You could change this R to an H. Doesn't really matter. Things like that. But behind that all is a great way to start thinking about dynamic programming. So hit like if this was useful.